Okay, in this presentation we are going to look at non-parametric tests for two independent samples. Now there's a couple of different procedures that we can look at, or we will look at over the course of several videos. The one I'm going to look at in this particular video is called the Wilcoxon rank sum test. The reason is it's just actually just sort of easy one just to sort of ease ourselves into this sort of thing. There are more complicated ones that we can use later on that would be suitable for this example, but again I'll just sort of go with an easy one to start off with. Okay, so a randomized experiment was carried out to test how well ethanox, a gas made up of 50% oxygen and 50% nitrous oxide, performed in reducing pain during a minor surgical procedure. 20 patients were randomized to receive air, 10 patients, and ethanox, 10 patients. So we have 10 patients each, 10 and 10. Okay. So immediately after the procedure, the patients use a score of 0 to 100, should be a little hyphen there, to record the level of pain that they suffered during the procedure. And here is a tabulation of their results. So two independent samples. Okay. So this person here suffered no pain. Okay. Just as a remark, this is the lowest person there. So on the minimum, the lowest value there, we're just going to assign that a value 1. Just as a remark, the highest value there seems to be 80, so we'll just actually mark that off as 20 there. Essentially what we're going to do is just sort of rank them a little bit, okay? Now this just takes a little bit of time to go through it, okay? So the second lowest value there is 2, the third lowest value is 3, next value then is 4, and so on, okay? This just sort of helps just to sort of just look through it there, and from starting from the bottom, just count them out a little bit, okay? And you can go through them like that. So in a practical setting, when you're doing this in an exam paper, an exam situation, that might be a good way of doing it there. The way I do it on the screen is more so just to get the point across on the screen, which is not exactly how you might do things in an exam hall. Okay. So let's move on. In situations such as these, when comparing two independent samples of subjective scores, remember, these are subjective scores. Briefly discuss the advantages and disadvantages of using non-parametric rather than parametric tests. Now, essentially, this sort of thing here, these scores, these like this sort of thing comes up quite a lot in life sciences, in medicine, in clinical studies, and psychology, and so on. So these non-parametric tests sort of deal with a lot of data that is hard to model. Okay, so the parametric tests, the most famous one being the t-test, I suppose. T-test need assumptions about the distribution underlying the data. Often that it is normally distributed and continuous. Okay, that might not be the case in a lot of data you're working with in medical statistics. Data is in the form of subjective scores and unlikely to follow any common distributions, and two sets of independent data may not even be the same shape, location, scatter, or skewness. Okay, so you can't make any assumptions really about them at all, about how they're structured or how they're distributed and so on. So non-parametric tests allow simple characteristics of distributions to be compared with few or no theoretical assumptions, but however, having said that, they have less power when compared to the corresponding parametric tests in which the parametric tests are valid. If you can use a parametric test, if it sort of stands up, if the assumptions hold, then you're better off using a parametric test where possible. They therefore need larger sample sizes as well. Now, what we're going to do here is, of course, we're going to use a sort of pen and paper example. So we're going to sort of stick with a small sample size. I'm cheating a little bit, really, just to sort of make things a bit more practical for an exam, for a video like this, and what would be coming up in an exam situation. You probably would do this with software. Okay. Using an appropriate non-parametric test to determine whether there is evidence that the pain scores differ. Okay, that's an important word there, differ. That actually sort of leads us to sort of say two-tailed. Okay, so you would express the null hypothesis as they don't differ, and the alternative hypothesis as they do differ. Okay. So that's just as simple as that. Now, there's actually how you correctly state the mathematical statement regarding the null and alternative hypothesis is in relation to a locational shift. But essentially, are they the same? Is there any effect at a practical level? Is there any difference? Is what we're looking at, or is one better at alleviating pain than the other, or does it make any difference? Okay. Explain your conclusions in a manner appropriate for a doctor to understand, including a comment of the implication of the sample size that may have on your conclusion. Okay. Now, so what I'm going to do here is I'm going to use the Wilcoxon rank sum test, okay, and just to remark, there's a different test called the Wilcoxon signed rank test, which is not appropriate here at all. It's for paired data. But something that you might use, and in fact I will do in a different video, is the Mann-Whitney-U test, which is essentially a bit more calculations are involved there, okay? Now, this is a non-parametric test to sort of see is there any difference between, in terms of the location between one and the other. So actually, I shouldn't have really specified that. Is there any difference, yes or no? The reason is that there's a very subtle way of correctly explaining what the null and alternative hypotheses are for these tests, okay? That at a practical level just sort of says, does the ethinox help, or does it make a difference, yes or no? Okay, but it's correctly in relation to a mathematical property of the distribution called the location. That is what the test is about. I won't get into that there. Well, it is actually important, but it's a sort of theoretical thing there, so it is just a sort of remark that it is what they call the null hypothesis, and the alternative hypothesis is in relation to a thing called location, which is sort of essentially a measure of centrality. Okay, again, there's a subtle but strong point to be dealt with there, but I'm not going to do it in this video. Okay, now this test uses simple ranks to compare two samples in which the observations are not paired. Just to remark that it's not paired data. Okay, we use a different procedure there. N1 and N2 are the sample sizes. Just as a remark, it's very important to actually just keep track of your notation, particularly with these non-parametric tests. And you'll see that when you're sort of calculating test statistics and so on for some of these tests, that there's quite a lot of calculation goes into them, okay? And quite often that there's sort of conventions. For example, N1 is always assigned to the smaller of the two sample sizes. Okay. First, rank all 20 items as follows. So this is what you should have done previously. So it's just sort of split that there into two. Okay. Or this is just to sort of fold it over on itself. So here are our 20 values in ascending order. Okay. Here is the groups that they're associated with. Okay. Really, I'm just reworking what I've done in the previous, or just previously, when I sort of started to look at the data. Just as a remark there, you don't really have to do this, but it does actually, in an exam situation, pay just to sort of show where your workings are, because that is a very important matter in an exam situation. Not just get the right answer, showing where you get the right answer. Okay. So essentially what we do here is that we have the ranks there, okay? So this, the lowest value there is 1, 2, 3, 4, and so on, all the way up to 20, okay? Now, so what we're going to do here is just sum up all the ranks that are associated with the ethinox there. So E, so we have 1, 2, 4, 5, 6, 7, 8, 9, 10. Sorry, I think I've got one extra there. All right, no, that's all 10 there, yeah. Okay. So just sort of collect them all up and add up all of those ranks there. So if I added them all up, I should get 81. If I was to add up all of the ranks for A, it should be 129. I can just sort of calculate them out there, do it the same way, but also the sum of the ranks should be the sum of 1 all the way up to 20 added up, which is, you can't figure that out, it's 210. So what is the difference between 81 and 210? It's 129. Okay. Now, two-sided test. Okay. So the way the tables I use are distributed or sort of work, that they sort of work on a one-tail basis. Okay. So essentially what I have to do here is go to the 2.5% set of tables here. Now this is actually very important, just as a because different textbooks and different statistical tables work differently. So I just be very, very careful about how that would work there. Okay. So the cell I'm looking for is 10 and 10. Those are the two sample sizes there. Notionally, that's the smaller of the two, N1. Okay, and N2 would be the larger of the two. But in this case, it doesn't really matter. Okay, but you know, just to sort of be careful about this. It was just we sort of got lucky here that they're both the same sample size. Okay, now, so I have this at the back. Okay, so this is my, I didn't actually write it in there, but this is my alpha equals 0.025 tables there. Okay, so essentially what I should do there is, or I should have made it a bit clearer on this here. So essentially N1, which is the smaller of the two, and N2, which should be the larger of the two, 10, 10, go out here, 78. Okay, so this is a two-tail test with alpha, the significance level, just picking 5% significance level, which is sort of what would be usual in undergraduate statistics. And so the answer we get there, when we look at it there, is 78. Okay. So I actually have different tables there. That is, sorry, a little typo there. Let's not look at that. But this is the 0.05, and this will be what we would use for one-tailed test. That's not how you spell tailed. Which is not what we're looking at here. Okay. So the test statistic we're looking at is essentially 78. So at a 5% level, we cannot reject the null hypothesis that the scores. We cannot reject the null hypothesis that the scores do not differ. Okay. So just a quick remark about the Mann-Whitney. I think I sort of covered that point already. Okay. Using a 10% level, which is looking at the other tables, just sort of really as a remark. That's just sort of, I'm going to sort of disregard that. Okay, so overall, we do not have enough evidence to say whether or not there's an advantage for Ethinox, so use a larger sample size. Okay, so just to sort of quickly remark, essentially what should happen there is that the it has to be less than this value here. That's just something we need to test. Is our test statistic less than our critical value? Okay. Now, just actually, that's a little bit different from when you deal with t-tests and so on, where you're actually looking for the test statistic to be greater than the critical value. That's not how it works here. It actually has to be less than the critical value here. Okay, so because we want it to be smaller, further away from the center, if you get me. So it has to be lower than 78. It has to be as low as under 78 as much as possible to be as the two, for there to be as much of a difference. Okay, so that's just how to interpret a test statistic. Is the test statistic less than the critical value? Okay, which is a little bit different from t-tests and so on. All right, we'll leave it there.